For over a century, energy extraction was defined by brute force. It was a period of heavy iron and extreme manual labor, where success depended on human endurance against the Earth's raw pressure. This era was inherently reactive. Because control was manual, operators had to wait for a gauge to drop or a valve to fail before they could provide a human intervention. Global markets now require a level of safety and efficiency that a fragmented, human-speed system cannot sustain. The margin for error has narrowed to the point where manual reaction is no longer a viable strategy. To meet these demands, the physical machinery of the past cannot simply be monitored. It has to learn to process data and adjust its own behavior without waiting for a prompt. We are moving past digital automation, which still relies on pre-programmed human instructions, into the realm of fully autonomous operations. OmniPetro is the architecture of this shift. It functions as a singular, connected intelligence rather than a collection of separate software tools. The network links physical field operations and refining facilities directly to the fluctuations of global financial markets. This means a sudden shift in energy demand on one side of the planet can trigger a calculated, autonomous physical adjustment to a pump thousands of miles away. At the center of OmniPetro is an AI-driven system that processes billions of signals to make high-speed operational decisions. This chart shows how global market demand metrics directly manipulate the output levels of a centralized energy grid. The system balances local extraction rates against real-time profitability and logistical bottlenecks. This schematic shows how the system handles the energy transition, balancing traditional hydrocarbon production with incoming renewable energy streams. Simultaneously, the AI tracks carbon output, identifying specific nodes of inefficiency and applying algorithms to reduce energy waste. By combining these efficiency gains with the strategic use of renewable inputs, the system creates a data-driven pathway for facilities to reach net zero status. This intelligence extends to remote physical infrastructure, such as this offshore platform, becoming self-optimizing fields. Individual units, like this isolated pump jack, no longer wait for a central command. They actively monitor their own reservoir health and internal flow rates. In complex networks of refinery piping, the infrastructure silently adjusts its own pressure and speed. This self-regulation reduces mechanical wear and tear without human oversight. The physical field has become a responsive mechanism that adapts its behavior in synchronization with the conditions of the Earth. To maintain these autonomous environments, a new frontline team has emerged: the digital workforce. Autonomous drones act as the system's eyes. They scan high-risk structures like this active flare stack to find microscopic anomalies invisible to the naked eye. These units deploy automatically from charging racks, executing pre-programmed flight paths without the need for a remote pilot. Ground-based robotics act as the system's hands. This quadruped unit uses an advanced sensor array to navigate complex terrain and perform mechanical inspections. This synergy between robotics and central AI creates a continuous feedback loop. It allows for technical maintenance while keeping humans out of hazardous zones. If the physical field is capable of managing its own execution, the role of the traditional control room must change. The frantic, alarm-driven atmosphere has been replaced by the Intelligent Operations Center. These sites focus on high-level data trends rather than individual mechanical failures. Operators here use live digital twins of their facilities to oversee the broader heartbeat of the global energy network. Human workers are shifting away from direct mechanical operation. Their work now involves managing the logic of the AI, setting the operational parameters, and supervising the system's learning process. Humans are responsible for ethical oversight, long-term economic planning, and high-level strategy, while the machine handles the moment-to-moment execution. A connected autonomous ecosystem introduces significant vulnerabilities. This visual representation shows how the network must use adaptive firewalls to neutralize cyber intrusions in real time. Maintaining this vision requires unbreakable cybersecurity, rigorous testing of AI reliability, and physical resilience against the extremes of a changing climate. OmniPetro is a synthesis of human judgment and machine execution, linking physical energy hardware and autonomous robotics into a single continuum. This network provides a model for an energy industry that is both highly autonomous and operationally sustainable.